So we learned how we can improve the thermal efficiency of the gas turbine. And the answer is that yes, by using regeneration, we can improve the thermal efficiency. Let me write this down again. Regeneration helps us to improve the thermal efficiency. But there's another factor that we have to think about in terms of performance of gas turbine. So the another thing that we have to think about is there any possible way to increase the net power output? Again, if you think about net work of the gas turbine, that is difference between the turbine work minus compressor work. So what this equation tells us is that in order to increase the net work, what you have to do is that we have to increase the turbine work and we also decrease the compressor work. Then how can you make it happen? So here comes the motivation of the concept of reheating and intercooling. Then what is the physics behind that concept? So now let's go back to the simple gas turbine with one compressor and one turbine and one combustion chamber. And now we know that is drawn as that. But if you really think about the constant pressure curve, the key feature that we have to focus on now is that how they are diverging between two constant pressure curves as we increase the entropy. So what it means is that if you look at that, the gap between these two curves, okay, is getting bigger as we move to the right side. So this value is smaller than this value, or the difference between these two values at higher temperature or higher entropy case is always bigger than the gap between these two curves at lower temperature cases. Okay, so what I can draw is this. So if you just try to extrapolate this curve, then we have this kind of trend. We have bigger and bigger and bigger gaps as we move to the right, and smaller and smaller and smaller gaps as we go to the left. Okay. So, graphically speaking, in the TS diagram, the gap, the distance between two curves here, like for the example from this point and to this point, graphically represents that qualitatively the amount of work produced by expansion if we go to this way. Okay, or in that case, this gap means the amount of power we need to run the compressor, and here the smaller gap means is better. On the right hand side, the bigger gap means is better because we can have more power output from the turbine. Okay. So then let me just write one more curve, one more line, which is the kind of design restriction. So we don't want to exceed the temperature, the maximum temperature bigger than this value. So that is T max. Again, in order to protect the blades of the turbine. So what I can think of is that now, in order to make more turbine power, okay, we really want to push this vertical line that is going to turbine work to the right side, so we can move to this side. Okay? So how can we make it happen? What if we have additional turbine? And what if we have secondary combustion chamber? So now instead of having one big turbine, from this point all the way down to this point, so that is what would happen if we have only one turbine, like a big turbine. But what if we have two turbines? Okay, such that the first turbine only has expansion from this point to certain point in the middle. Okay, then we have secondary combustion chamber to heat up the gas one more time to increase the temperature up to this point. Okay? Then we have additional turbine to expand this gas to the secondary turbine here. So now we are talking about two turbine systems instead of one turbine. Same thing. What would happen if we have two compressors instead of one big compressor? So what I mean by this concept is, what if we replace this one big compressor to two small compressors? Then the first compressor compresses your air from 1 to somewhere in the middle. Okay. And now we try to cool the air down one more time until it goes to the same temperature of T1. So in order to compare the simple gas turbine with a gas turbine with two turbines and two compressors, let's try to make an index for each state. So now we have from 1 to 2, and now we have 3, 4, 5, 6, 7, and 8. Okay. Then let's try to put an index for that as 2 prime. Okay. And now that we have 6 prime. So obviously, what happens between these two cases here and here, because the curve are diverging, what you can see is that 6 to 6 prime is smaller than the work of turbine between 7 and 8. Okay, because we push this line, vertical line, to the higher entropy case. Same way here, if you just compare this gap distance and that gap distance, we can say that the W at 3 to 4 is smaller than W to 2 to 2 prime. Okay. So that is the effect of intercooling, and that is effect of reheating that needs two-stage turbine. Okay, and that is a two-stage compressor. Then let's take a look at the entire process diagrams in a TS diagram. So by having two turbines and two compressors, what you can see is that there is a certain increase of the area surrounded by those processes. Now, if I try to draw the highlight of the area of a two-stage gas turbine system, what you have is this all shaded area. So apparently this area is bigger than the area with a single compressor and turbine system, which can be highlighted as this. So obviously, when you have two-stage gas turbines and two-stage the compressors with the reheater and intercoolers, or even you can expand more to have multi-stage gas turbines and multi-stage compressors, then we basically have more and more area of WNet. That means we can increase the net amount of power for those kind of multi-stage gas turbine systems. However, what you have to think about is that what happens to the amount of heat input to that multi-stage gas turbine system. As you clearly see here, then we actually have more heat input. So for example, we have to have more heat input from 4 to 2 prime. So that is kind of increase of heat input that we need to run this gas turbine. Okay. And also we have additional heat input through the reheater. So there should be additional heat input. And also there should be certain additional heat loss during this intercooling system and additional heat loss from 8 to 6 prime. Now, with those kind of general point of view description, so let's take a look at how we can do more like a thermodynamic analysis. So this is the schematic diagram of two-stage gas turbine, where we have two compressors, and in between we have intercooler, and we have a main combustion chamber, and we have two turbines, and between two turbines we have reheater. Okay. Now, in terms of compressor work, we have two compressors. So the first term should be compressor 1, and the second one is from compressor 2. Same way, the expansion work should come from two turbines. One is turbine 1 and the other one is turbine 2. Now, in terms of heat input, then we have two heat input components. One is from combustion chamber, then the other one is from reheater. So, as we discussed, more likely qualitatively using the TS diagram, by doing thermodynamic analysis of this compressor work and expansion work, we can clearly calculate the value of net work, okay, for two-stage, and this one is greater than the net work for single stage. However, we also have increase of the heat input for that two-stage gas turbine. So as a result, usually the thermal efficiency for two-stage is lower than the thermal efficiency of single stage. So by sacrificing thermal efficiency, then we can gain more net work. So that is what you can see from this two-stage gas turbine. So is there any way that we can improve the thermal efficiency for that two-stage gas turbine? And we already learned about how to improve the thermal efficiency. And yes, we can improve the thermal efficiency for the two-stage gas turbine by integrating the regeneration for that system. So that is usual two-stage gas turbine system. So by having multi-stage compressors and multi-stage turbines, but by having additional regenerator or additional heat exchanger, we can still improve the thermal efficiency. So by having regenerator, we can improve the thermal efficiency, but still by having reheater and intercooler, we can have more net work.
In this lecture, we learned about two realistic features of a gas turbine. So based on the ideal Brayton cycle, we considered two realistic features. One is a pressure drop in a heat addition process or heat transfer processes, and another one is irreversibilities in compressor and turbines. Particularly, we have to take care of the irreversibilities in a compressor and turbine. Okay, so now for this end, we use the isentropic efficiencies. So the isentropic efficiency that we learned in lecture note 21 actually explains how much realistic the operations of compressor and turbine should be considered. We also learned the regeneration. So the purpose of using a regeneration is to preheat the compressed air from the exhaust gas to improve the thermal efficiency of overall gas turbine system. Also, there is another way to boost up the power output, which is to use the reheating and intercooling for second stage gas turbines. So instead of having single compressor and single turbine, we can have multi-stage compressors or multi-stage gas turbines. And in between, we should put intercooler and reheaters. So by having those two-stage or more stage gas turbines, we can increase the net power output. But in return, usually the thermal efficiency is getting worse. So in order to compensate this decrease of thermal efficiency, many times we integrate the regeneration scheme or regenerator with than multi-stage gas turbines. We don't really have to have both reheating and intercooling. Sometimes we only use reheating instead of still while we only have one compressor. So we learned about those, how we can expand the gas turbine for power generation. Thank you so much for your time and your attention for this lecture. So in the next lecture, we are going to talk about the Rankine cycle. So for now, we have discussed how we understand gas power cycles. But from the next lecture, we are going to talk about how we understand the power cycle when we have working fluid, not a gas, but a water. Okay, so that is a base thermodynamic model of usual steam power plant. Again, thank you so much and have a wonderful day. Bye-bye.